Hi, so we are about to start the second part of the talks in this morning. So the first talk is by Apurba. He will be talking about twin radio bursts. Over to you, Apurba.
Thanks, Bhaswati. And thanks for the invitation to give a talk here. And I'll be talking about the curious case of twin fast radio bursts. I'm from Astron and also from ICRA Curtin University, and I am part of the CRAFT collaboration. And I believe you have had enough introduction to fast radio bursts. So I'll skip my first two slides and go straight in the survey that I am part of, the Commensal Real-Time Escape Fast Transient Survey, which we call CRAFT. It has 50 plus team members from 10 plus countries, over 20 plus institutes all over the world. And the survey uses the Australian Escape Pathfinder, which is located at the CSIRO Murchison Radio Astronomy Observatory in Western Australia. It's equipped with phased array feeds on all individual 36 antennas. And the phased array feed allows 36 individual beam forming on the sky, which gives us a field of view of 30 square degrees. And the Commensal Real-Time Escape Fast Transient or CRAFT survey is a real-time search for dispersed radio signals, where the detection triggers recording of raw voltage data from individual antennas. And when we have raw voltage data, we run it through our post-processing pipeline, which is called the CRAFT Effortless Localization and Enhanced Burst Inspection or CELEBI pipeline, where we can offline correlate and image the FRB to get sub-arc-second localization on the sky, which gives us enough accuracy to identify not only the host galaxy of the FRBs, but also where in the host galaxy did the FRB occur. And we can also use the localization information to make phase coherent beams, which gives us full polar high time resolution outputs, which can go down in principle to as small as 3 nanoseconds. So with the introduction, I'll go straight to my talk. So what we have seen is that the FRBs look very different in high time resolution, and there is a diverse there are diverse properties of fast radio bursts at time resolutions of millisecond or sub-millisecond. And the time frequency structure in general is complex, so is the polarization behavior, some of which are probably attributable to propagation effects like scattering, scintillation, and other things. However, we found two FRBs in our current sample, FRB 181112 and FRB 210912, which look surprisingly similar. For the rest of my talk, I'll mainly describe how similar these two FRBs are. First of all, just a brief introduction to these two FRBs. These two FRBs occurred at different parts of the sky and 3 years apart. They have different dispersion measures and different burst fluences. For the older FRB, 181112, we have a host galaxy and we have a redshift measurement, which is 0.4755. For the newer FRB, 210912, we still do not have a redshift measurement. I'll come back to that later. When we looked at the burst profiles, which in the observed frame look like the left-hand side plot here, we found that they both have two subbursts. The primary one, or the first one, is a stronger one, and the following one is weaker, and they have different time scales. But surprisingly, if the time axis is renormalized by the separation between the two peaks, which I am calling it delta T AB, then the relative time scales match very well. Quantitatively, in the bottom of the slide, I am showing the ratio of the FWHMs of the two subbursts A and B, which is same within the error bars for two FRBs. The separation of the peaks are 0.81 millisecond and 1.27 millisecond, so they are different in two subbursts. However, the FWHM of each subburst relative to the peak separation is again same within the error bars. So we know the redshift of 1FRB, which is 181112. If the redshift of the unknown one, which is 210912, is exactly 1.33, then these two bursts would have identical rest frame timescales. And this redshift, the required redshift of 1.33, is actually quite consistent with the redshift from DM. So there is a relation which I'm pretty sure you have heard about in this conference between the cosmological dispersion measure and redshift. And using that, we get a rough redshift estimate of 1.2 plus minus 0.2, which includes our required redshift. However, this is not all the similarities between these two FRBs. In the top panels, I am showing the rotation measures for individual subbursts of both these FRBs. So for both these FRBs, we find that the rotation measure is different in two different subbursts. And while the absolute values of the rotation measures are different in these two FRBs, the differential rotation measure, which is the difference between RMs of subburst A and subburst B, is approximately the same. They are actually same within the error bars, approximately 15 radians per meter square. More surprisingly, if you measure a rotation measure within the first subburst in a time-resolved fashion, they both show non-monotonic behavior, which is qualitatively similar in both these two FRBs. And this short time scale variation of RM at time scales of sub-millisecond is actually not very common in all our FRBs. Only a few of them show this behavior, and both these two FRBs are among them. And when we looked at the polarization position angle across the primary subburst of two FRBs, both of them show the characteristic PA swing or sweep of PA across the primary subburst, although in different directions. Now, the question is, are all these similarities between these two FRBs is a pure random coincidence, which in principle cannot be ruled out. However, because similarities are a bit hard to quantify, it's difficult to estimate the probability of this random coincidence. And the other possibility is that they have very similar progenitors, and that's why they share all these unique properties. That brings us to the question, what could be their progenitors? So when we looked at FRB 210912, which is the later FRB, in a time-resolved manner, we see that its two subbursts, A and B, show qualitatively opposite manner of PA sweep, which can be broadly described by a simple rotating vector model, where the PA traces the projection of the magnetic field on the sky plane as a neutron star or a compact magnetized object rotates on the sky. And we got consistent solutions for both the subbursts, which comes from a magnetic obliquity of about 59 degrees, which is the angle between the rotation axis and the magnetic axis of a neutron star or any magnetized object, and an impact angle of 17 degrees for the primary subburst, which is the angle between the line of sight and the magnetic axis. Now, if there is a big if here, the progenitor of this FRB is really a neutron star, where we see emission from both the poles. That will mean that there are two neutron stars which rotate with rest frame spin periods of about 1.1 millisecond. However, before that, let's go back to the redshift measurement of 210912, which is the letter FRB. For this FRB, we initially did not have a host galaxy, and the redshift DM relation gave us a rough redshift of about 1.2. And just to remind you, to make the intrinsic timescales identical, we require a redshift of 1.33. So the easiest thing would be to find the host galaxy of this FRB and measure its redshift, and then confirm this. So initial observations, deep observations with the VLT did not identify any host galaxy at the location of the FRB on the sky. And the upper limit on magnitudes was in R band it was 26.7 and K band it was 24.9, which are 5 sigma limits. And then we went ahead and wrote a proposal to JWST to find its host galaxy because it's so faint. And the initial JWST NIRCam imaging revealed a very faint host galaxy, which has a apparent magnitude of 29.1, and it makes it the faintest FRB host so far detected. We do not have good spectroscopy results yet. We are waiting for that. If the spectroscopy result gives a redshift of 1.33, then that will mean that these two FRBs are probably coming from two objects which are rotating at the same intrinsic speed, rotation speed, which may mean that there are a class of FRBs which are originating from very fast rotating neutron stars. And this rest frame spin period of 1.1 millisecond is actually shorter than the shortest known spin period of a millisecond pulsar, which basically means that if these FRBs are being originated in neutron stars, then their progenitors are rotating faster than the fastest known rotating millisecond pulsar. And the spin period, or the infart spin period of 1.1 millisecond is actually very close to the shortest possible or shortest allowed spin period of neutron stars, which is about 0.84 millisecond. So with that, I'll leave you with this slide. And if you have any questions, I believe you can ask over Slack or probably now. That's all. Thank you.
Thanks, Apurba, for the talk. Questions for Apurba?
Very nice talk and very interesting observations. So I want to suggest a slightly different interpretation, and I will say why. So if you have a 1 millisecond period for the neutron star and a magnetar strength field, which is needed to power FRBs, then you spin down in just minutes. And so that is unsustainable because on that time scale, the region is completely opaque to FRB emission. So there's no way to get FRBs out of this kind of region. So what I would like to suggest as an alternative interpretation, which is something we discussed in a paper that we wrote earlier this year with Pawan Kumar, is that instead it's still something like a rotating vector model, but the period is longer, and what you are seeing is just a sort of hollow cone emission, where the separation between the two bursts that you see, those twins, is actually the duration of the polar cap sweeping through the line of sight, and the individual durations of each one of those instances where the polarization angle is going up and down is just the width of this hollow cone. And then you can do it with a spin period that is longer, maybe even closer to a second, and that makes it consistent with all the other constraints that we have in terms of optical depth and so on. So I wanted to know what you think of that possibility.
Yeah, I completely agree that this remains a possibility. And right now there is nothing to basically rule this out. However, my question would be for you, what makes the rest frame time scale so identical? So if it is just a hollow cone, you have to somehow make the hollow cone identical when it is observed from Earth in the rest frame. So it's kind of the angular size of the cone, and I think the ratio between the angular size of the cone and the spin period, intrinsic spin period.
So what is the ratio between the two, those two subbursts? The ratio of their durations? They're both some fraction of a millisecond, right?
Yep.
But how close are they to each other in time?
In observed frame, one is 0.8 and the other one is 1.27.
Yeah, so this is factor of order 2. That's easy to accommodate. One can show, we can maybe talk about this later offline, that for a typical spin period that we expect to dominate the FRB population, the time of the polar cap sweeping across the line of sight is exactly of this order of 1 millisecond or maybe slightly longer. So that much is relatively natural, and yeah, we can talk more offline if you're interested.
Yeah, sure. And thank you so much for your comment. Let's talk offline about this.
Thank you.
More questions for Apurba? Maybe I can ask one because so you said like about the rest frame Z, these two FRBs have same rest frame Z. So from the population of known FRBs, can you like extract such twins, like any more possibility of getting such twin FRBs? They may not have these two subburst structure, but even then.
Yeah. So the identification of these twin FRBs was made based on a few properties. But one is the time scale. The other one is differential rotation measure, and then rotation measure variation across subbursts. All these are pretty rare in at least our sample, and we don't have enough signal to noise ratio in all FRBs to actually do this, to measure rotation measure as a function of or in small time bins. So we cannot rule out that there are other FRBs that belong to this class, but we have not have any convincing evidence for that yet.
Yeah, so this you do not have, but you have the Z values. So just comparing Z values, some candidate twins where you cannot confirm.
Yeah, there are candidates which are approximately similar, not exactly same, but there are other candidates. But because we cannot really go down in measurement of rotation measure, etc., and the signal to noise ratios are not very large always, so we can't really confirm yet.
Okay. More questions for Apurba? And online participants, do you have any question? Please unmute and ask if you have. Okay, if not, then thanks Apurba for interesting talk.
Thank you so much.